Hi everybody, welcome to this course on Internet Technologies. I'm Vardan and today we'll be studying about the IP datagram and IP fragmentation. Let's start with a quick recap of the Internet protocol, specifically IPv4, which remains widely used even today. IPv4 is a connectionless, stateless protocol, which means it doesn't maintain any history of previous packets or connections. Each packet or datagram is treated independently, and routers only make forwarding decisions based on the information in the current packet. Every IPv4 datagram includes a source IP address and a destination IP address, which are used by routers to decide where to forward the packet. IP sits at the internet layer in the TCP/IP stack and receives data from the upper layer protocols like TCP or UDP. It then encapsulates it by adding its own header and passes it down to the network access layer. And an important detail here is that the minimum size of an IPv4 header is 20 bytes, but it can be extended with optional fields. These headers carry control information, which is necessary for routing, delivery, and fragmentation. We'll look at the structure of this datagram in detail. Here you see the complete layout of an IPv4 datagram. At the top of the header, fields like version, header length, and type of service are present, followed by critical fields like total length, identification, and fragmentation information. Further down, fields like time to live, protocol, header checksum, and the essential source and destination IP addresses are included. If required, the header can also contain optional fields like source routing and padding, making the header size variable. After the header comes to the data payload, which carries the actual information from the TCP, UDP, or other protocols. We'll now break down the header piece by piece so you can see what each part does and why it matters. Let's begin with the first four fields. Version specifies the IP version. For IPv4, this value is always 4. Header length indicates the length of the IP header in 32-bit words, and the minimum value is 5, which means 5 times 4 is 20 bytes when no options are present. Type of service suggests how the datagram should be handled in terms of priority and quality, allowing differentiated services like minimizing delay or maximizing reliability, and it's rarely used nowadays. Total length indicates the complete size of the datagram, including the header and the data, and the maximum possible value for this is 65,535 bytes, though most networks enforce lower limits, which are called MTUs, which we'll discuss in fragmentation. Next, we have some crucial control fields. Time to live prevents packets from circulating endlessly in case of routing loops. Each router that forwards the packet decreases this value by 1. If time to live reaches 0, the packet is discarded and an ICMP error message is sent back. Protocol tells IP what type of payload it's carrying. Common values include 6 for TCP, 17 for UDP, and 1 for ICMP. This helps the receiver know how to process the encapsulated data. The source IP address is the IP address of the sender, and the destination IP address is the IP address of the intended recipient, and they are 32-bit each. These four fields together make sure a packet knows where it's coming from and where it's going, how long it can stay alive in the network, and what type of data it's carrying. Options is an optional field used for advanced functions like source routing, where the sender specifies a route the packet must follow, and it's again rarely used, but it's supported for backward compatibility. And header checksum validates the integrity of the IP header only, not the data. And the IPv4 header checksum is calculated by taking the entire header, treating it as a sequence of 16-bit words, and adding them together using ones complement addition. After the sum is computed, you take the ones complement of the final result, meaning you flip all the bits and store it in the checksum field. At every hop, the router recalculates the checksum because fields like the time to live decrease, and if the new calculated checksum doesn't match the value carried in the header, it means the header got corrupted in transit and the packet has to be discarded. Now, three fields we'll explain fully in the fragmentation part. The identification, which is a unique number assigned to each datagram. So fragments of the same packet can be identified and reassembled. Flags is a 3-bit field, and flags control where a datagram can be fragmented. It includes a don't fragment bit and a more fragment bit. And fragment offset indicates the position of a fragment within the original packet. And these fields are vital for handling fragmentation, which we'll cover next. So IPv4 networks have a limit on the maximum size of data they can transmit in a single frame, which is called the maximum transmission unit, or MTU. If an IP packet exceeds this MTU, it must be fragmented into smaller pieces. Each fragment is treated as an independent IP packet carrying its own IP header and appropriate values in the identification, flag, and fragment offset fields. The fragmentation process ensures that large datagrams can still be transported across networks with smaller MTU limits. The challenge lies in making sure fragments are correctly labeled and ordered so the receiver can reassemble them without loss or corruption. Modern IPv6 eliminates fragmentation by routers, but in IPv4 it remains an essential mechanism. So there are two types of fragmentation approaches used in network design. One is transparent fragmentation, in which packets are fragmented at the entry router of a network and reassembled before exiting. The other is non-transparent fragmentation, in which packets are fragmented wherever needed as they travel through various networks. And the receiver assembles all the fragments once they arrive. In this diagram, you can see a network system and packets enter a network through a router. Depending on the network's MTU, the router might fragment the packet before forwarding it. Each method has its pros and cons, which we'll explore in detail next. Here's a visual of transparent fragmentation. Notice how the router fragments the packet when it enters a network with a lower MTU. Then all fragments are reassembled before they exit that network. The advantage is simplicity for the receiving device. It only gets complete packets, but it increases the workload for intermediate routers as they need to manage fragment storage and reassembly. In modern high-speed networks, this approach is hardly used due to the performance limitations. Now, a few key details about transparent fragmentation. Fragments are reassembled within the network before exiting. Transparent fragmentation ensures end host receives full datagrams, and there is high processing load on intermediate routers, and this approach also requires routers to maintain fragment buffers, which can get very complicated under heavy traffic. And its biggest drawback, however, is poor scalability. As network speeds and traffic volumes increased, this extra overhead made transparent fragmentation impractical. And that is why most modern networks rely on non transparent fragmentation. In non-transparent fragmentation, the packet is fragmented whenever it crosses a network with a lower MTU. These fragments then travel independently through the network and are only reassembled at the final destination. This offloads the burden from routers and simplifies network design, as routers only need to forward fragments without holding or managing them. In this diagram, you can see how fragments move independently through the network, possibly even taking different routes before arriving at the destination, not necessarily in the order they were sent in. Now, non-transparent fragmentation offers several advantages. First is that routers don't have to buffer fragments or reassemble them. Then fragments travel independently, which increases flexibility. And this approach is better for scalability and for high speed and high traffic networks. And its drawbacks include the risk that if a single fragment is lost, the whole datagram must be discarded and retransmitted by the sender. Also, the end host must handle reassembly, increasing its workload slightly. Despite these, non-transparent fragmentation is what IPv4 networks use today. It remains efficient, scalable for the decentralized packet switched architecture of the internet. Now, when fragmentation occurs, IP uses three fields to manage it. One is identification. So each datagram gets a unique ID. Fragments of the same datagram carry the same ID. And the flags, all of them are not used. There are three flag bits, but only two of them are defined. One is more fragment bit. It is set in all fragments except the last one. And the don't fragment bit, which prevents fragmentation entirely. The third is fragment offset. This tells the receiver where this fragment belongs in the original datagram, and it is measured in multiples of 8 bytes. With these three fields, the receiver can track, reassemble, or detect missing fragments of a datagram. Alright, let's walk through this example to understand exactly how fragmentation works in IPv4. We start with a single IP datagram whose total size is 1020 bytes. Out of this, 1000 bytes is the actual data payload coming from the transport layer, and 20 bytes is the IP header. Now, this packet has to travel through two different networks. First one, called N1, has maximum transmission unit or MTU of 620 bytes, and the second one, N2, has an MTU of just 400 bytes. When the packet reaches the first router at the entry point of N1, it checks the MTU. Since the total size of our packet, 1020 bytes, is larger than the MTU of 620, it has to fragment the packet. Now remember, each fragment needs its own IP header of 20 bytes. So the actual data we can fit inside each fragment is 620 minus 20, which leaves us with 600 bytes of data. The router now splits the original data into two fragments. The first fragment takes 600 bytes of data and adds a 20 byte header, making it a total of 620 bytes, which fits exactly within the MTU. This fragment is marked with a more fragment or M bit set to 1, indicating that more fragments will follow. Its fragment offset or FO is 0 because it's carrying the first part of the original data. Now 100 minus 600 leaves us with 400 bytes of data remaining. This forms the second fragment. It also gets a 20 byte header, making it a 620 bytes total. Its fragment offset is set to 600 divided by 8 because FO is measured in 8 byte units again. So 600 divided by 8 gives us 75. The M bit for this fragment is set to 0, indicating that it's the last segment for last fragment for this network segment. Both fragments now travel through N1 and reach N2, where the MTU is even lower, just 400 bytes. Now both the 620 byte and 420 byte fragments are too big for this network, so they need to be fragmented again. Let's start with the first fragment, which was 620 bytes total with 600 bytes of data. And if N2 allows only 400 bytes per packet and a 20 bytes header, we can fit 380 bytes of data. But here's the catch: the fragment offset is measured in multiples of 8. So the largest multiple of 8 we can take under 380 is 376 bytes. So we can create a new fragment carrying 376 bytes of data with a 20 byte header. Its fragment offset remains 0 and the m bit is still 1 since there's more data remaining. Then the remaining data in this fragment is 600 minus 376, which is 224 bytes. This becomes the next fragment. It gets its own header and an FO value of 376 divided by 8, which is 47, and an m bit of 1 because more fragments are still expected. Now moving to the second fragment from N1, which was originally carrying 400 bytes of data. Using the same calculation, the maximum data per fragment again is 376 bytes. The first fragment of this part gets 376 bytes of data and a 20 byte header and an FO of 75 because the original FO for this piece was already 75. Its M bit is 1 because a little more data is left. Finally, the last piece is the remaining 24 bytes of data. It gets its own 20 byte header and an FO value of 75 plus 376 divided by 8, which is 47. So 75 plus 47 equals 122. Its m bit is set to 0, meaning this is the last fragment of the entire original datagram. When you add up all these fragments, 4 data parts and their headers, the total data transmitted becomes 1000 bytes of data and 80 bytes of header, making a total of 1080 bytes transmitted over the network. This example perfectly shows how fragmentation works dynamically across networks with different MTUs and how IP layers use identification, fragment offset, and more fragment fields to track and reassemble the data at the destination. With that, we've come to the end of this lecture. In the next one, we'll learn about the IPv4 address classes. Thank you for joining in, and I'll see you next time.